Hello again. We are continuing our study of lipids with section 15.3, and in this section we're going to talk about waxes and triacylglycerols, or you also see triacylglycerols as triglycerides. Anyway, these are both esters. Waxes are natural materials. They're very common in fruits, leaves, stems of plants. They prevent water loss, damage from pests. Waxes on the skin of certain animals also provide a waterproof coating. And it's interesting that we use waxes in pretty much the same way as waterproof coatings for cars and maybe tables and various things. And they do pretty much the same function. And actually the materials that we use are in some cases the same thing, as you'll see momentarily. Waxes are maybe the simplest of them. They're esters. You know what an ester is. It's a result of a reaction between a carboxylic acid and an alcohol, where you lose water and you form a chain or a bond between the oxygen of the hydroxyl group on the long chain alcohol and the carbonyl of the fatty acid. So when you do this, you see these are fatty acids, saturated fatty acids, and long chain alcohols, and long is pretty long, 14 to 30 carbon atoms. So these things are going to be very, very hydrophobic. And saturated fatty acids, straight chains, they're going to be solids. And so they're going to make a pretty decent coating. Here's some of the typical waxes. And as you see, you probably recognize all of these. These are all used for various, each one has kind of specific uses. Beeswax. I don't know if you've ever heard of the Australian instrument. The Aborigines, the early inhabitants of Australia, found these. They created a musical instrument out of branches of eucalyptus trees that had been hollowed out by termites, and they fit them with a beeswax mouthpiece, and they give you that droning sound that you'll see sometimes in commercials or television programs, commercials, or whatever, with an Australian theme. You'll hear there's this strange droning sound in the background. Well, that's a didgeridoo. Also has some other names. But beeswax is used for that too. There's carnauba wax, jojoba wax. And if you take a look at these structures, you'll see the carboxylic acid in beeswax. They're giving C16. Think about that. What's C16? Carboxylic acid. Palmitic acid, right? And the carnauba wax, well, that's a really big one. I don't know if we don't really have a I don't recall off the top of my head. It may be in there somewhere, but that's C26. That's a pretty big carboxylic acid. And it's got a C30 alcohol. And the jojoba wax, they're given a C20 carboxylic acid. That would be dodecanoic acid. Arachidonic acid, you should know, it's an unsaturated C20, but this one's saturated. So, and you see the uses are pretty similar across the board. So much for waxes. Let's move on to triacylglycerols, and sometimes you'll see triglycerides, as I've said. These are the way fatty acids are stored in the body. They're esters again. They're triesters. You take glycerol and you esterify each of the hydroxyls with a fatty acid, and you got a triglyceride. So it's similar to wax. It's similar to a wax, except that it's a triester instead of a monoester. And we named them by simply changing the glycerol, remove the ol to ill, change it to YL, and name the fatty acids as carboxylates. So you'll see what we have here. This is the triglyceride, triacylglycerol, that's formed from stearic acid. These things can be mixed too, by the way. They're not all going to be pure, esters of one single carboxylic acid. But in this case, for naming these things, for naming this one, we're using 3 stearic acid molecules in glycerol. And you see that 3 water molecules are removed. And by the way, for doing homeworks, there are, I believe there's a problem in there where you need to actually draw something, and you need to actually give all of these products. And I think that I know that I gave you links to a couple of videos on drawing these molecules, and you'll see how that works. And you'll need to be doing this. This is a balanced equation if you think about it. You're taking triglycerol and 3 stearic acid molecules, and you're forming the ester by removing that water molecule from between the alcohol hydroxyl and the carboxylic acid, and you're going to get the ester bond. Most of the triacylglycerols you see in nature are mixed, so they don't all have the same thing. But we do need to be aware that these exist. And all we're doing here is we're just pointing out that these things do exist. There are these are mixed triacylglycerols. And you see this one has 3 different fatty acids. And there are patterns to how these fatty acids are arranged, especially with regard to whether they're saturated or unsaturated in nature, but we don't go into those. That's topic of more advanced courses. Well, what do we use triacylglycerols for? Well, the main thing is energy storage. You may recall from a few lectures ago, a few modules ago, that the energy content of fats is actually pretty high. I'm pretty sure it was chapter 3, but it was early in the course where you actually needed to calculate the energy content of various foods. And you might remember the energy content of fats amounts to something like 9 kilocalories per gram, and that of proteins and carbohydrates, which can also be used for energy, is only about 4 kilocalories per gram. So the energy content of fats is pretty high, so it's a really good energy storage material. And that's one reason that animals that hibernate do store a lot of fatty acids in the form of triacylglycerols, which their bodies use to keep them maintain some metabolism, some metabolic rate, and keep them alive over the winter. So we can go on to a learning check here. You need to know some of these fatty acids, and these are in your text. What are fatty acids in the following triacylglycerol? Well, all you do is decide, are they saturated or unsaturated, and count up the carbon atoms in the chain. They all have a very similar structure. They're a carboxyl group with a carbon chain, which is either saturated with hydrogens or it's only carbon and hydrogen in that chain. There may be some double bonds. And you need to know the placement of how many double bonds there are, the placement of the double bonds, and also how many carbon atoms. So this one has a couple of different fatty acids. Looks like there's 3 different ones. Well, let's just work our way down. You see that CH2 in parentheses with a 16. So there's 16 atoms there. That's CH2 taken 16 times. So that's 16. That's going to be 16 carbon atoms, 32 oxygen or hydrogen atoms. And then you have the carbonyl carbon and the methyl carbon on the end. That's going to be 18. Well, it's an 18 carbon chain. It's saturated. It has to be stearic acid. So that's the first one. The second one, it's unsaturated. And if you count these up, you've got the carbonyl group. You've got 7 CH2s, which makes 8. Then you got a ninth one, the first double bond, 10th, the second double bond carbon. And then you have 7 plus it, that's 8 more. So that's an 18 carbon acid with 1 double bond. That's going to be, that's oleic acid. That's going to be oleic acid. And then this other one, this is 12 plus 2. That's going to be 14 carbons. That's going to be myristic acid. Let me see. That's how it's broken down. Drawing a structure. Well, they want you to draw condensed structures. You know what condensed structures are by now. They give you the analyze the problem, the strategy, the basic problem-solving strategy that they talk about. You're given the glycerol tripalmitoleate or tripalmitolein, and you need a condensed structure. Okay, well, you need 3 ester bonds. You know you have glycerol, so you're going to have to have 3 ester bonds, and you're going to have to arrange the bond in such a way that you've got the carboxyl group, the carboxyl carbon is bonded to the oxygen from the alcohol, or from the alcohol glycerol. So you know what the carbon skeleton is. You really just need to know the carbon skeleton, then you can put the carboxyl group on the other at the end of it, and then work with that. So here you have it, glycerol tripalmitoleate. So draw the condensed structure of triacylglycerol containing 3 molecules of myristic acid. Well, we already saw that myristic acid is C14, and when we look at this, we're really going to do the same thing. All right. We're going to these, let me outline this here. I guess I can't outline this here, can I? But you have, I think you can see the cursor. You should be able to see the cursor. So we're starting here, the top hydroxyl group, the top oxygen from the glycerol. You have, you're going to have the oxygen there, and you can put the carbonyl carbon from the carboxyl group. That's going to be C1. And then, well, then you just write out the rest of the chain. And of course, we've already told you that this is myristic acid, so that it's myristic acid saturated, and it's C14. So you've got this 1 carbon here, and then there's going to be 13 more carbons, and they're all going to be saturated. And that's going to be the same on every one of these hydroxyl groups. Actually, that's the way they have it. Difference between fats and oils. These things have a bad reputation. I think I saw something like that, said something like that earlier. But they do have definite uses. They're very important in metabolism. They provide most of our energy, or at least a very large proportion of it. There's different, depending on the activities, you might burn more carbohydrate and less fat, or more fat and less carbohydrate. The difference between fats and oils is largely melting point. Okay, fat's usually solid at room temperature, and oil is usually liquid at room temperature. An oil usually obtained from a plant source. There are oils, there are animal oils, fish oil, for example. And they're going to have a lot of oils are going to tend to have more unsaturated fatty acids. Although palm oil, coconut oil are coconut oil in particular, I know palm oil, I'm pretty sure this is true too, they have a lot of saturated fatty acid in them, which is a little bit odd for oils, but they have some low molecular weight, lower, like C6, C8, C10, 6, 8, 10 carbon fatty acids, which they're solid at room temperature, but the mixtures of these things, when you have several of these different compounds, the melting points can be a little lower. But so these are oils, but these are about the only ones. Coconut oil is, like I said, it's rare. Most oils have unsaturated fatty acids, a lot of unsaturated fatty acids in them. Soybean oil, canola oil, olive oil, all those. And they mention olive and peanut oil. Most of the fatty acids there are unsaturated, monounsaturated, and they have a lot of oleic acid in them. And in fact, olive oil and the word oleic acid comes from, oil in ancient Rome was olive oil, pretty much. Then you have corn, cottonseed, safflower, sunflower. There's others, peanut oil. Well, they mentioned peanut oil. There's a lot of these, a lot of different kinds of oils. These are all triglycerides. They're made of glycerin, which is esterified to fatty acids, and most of the fatty acids are unsaturated. And they mentioned palm and coconut oil are room temperature. They contain mostly saturated fatty acids, although they do melt at fairly low temperatures. They melt right around room temperatures, whereas these other solids, like the other animal fats, they melt a little higher, 40 degrees Celsius, somewhere around there, maybe in the 30s or 40s. And the melting point difference between fats and oils is pretty much the same. It's for the same reason as the melting point difference in unsaturated and saturated fatty acids. The packing of the ability to pack tightly and closer to have the dispersion forces between molecules is going to be a lot stronger because they can line up in more surface contact of the molecules in the saturated materials. So they're going to pack together tighter. And as you see, the animal fats, coconut and palm oils have a lot of saturated fatty acids in them. In fact, you'll see there's a slide here, which is actually it's going to be the next slide, where you'll see some of the relative amounts. So the same argument we used in explaining melting points of saturated and unsaturated fatty acids, we use to explain the melting points of oils and fats. There's a table which shows you the relative amounts of polyunsaturated, monounsaturated, and saturated. And you see coconut oil is fairly unique among it. Well, it's listed as a solid, so you would normally call it a fat, but they said fats are usually solids and oils are usually liquids at room temperature. Well, there are exceptions. Coconut oil is one. So you can see beef tallow has a lot of monounsaturated and a lot of saturated, very little polyunsaturated. Butter is pretty similar, but it is more saturated relatively, and coconut oil really doesn't have a great deal of polyunsaturated. Maybe a trace of these. And then you see canola, soybean, sunflower, corn, and most of these don't have a lot of some of them have a lot of polyunsaturated, some of them don't. You can see canola oil, olive oil and canola oil are really heavy on the monounsaturated, and canola, soybean, safflower polyunsaturated. Most of that's going to be linoleic acid, little bit of linolenic, but it does vary quite a lot. If you were to, there's others. Linseed oil is another one. It's used, actually it's used in painting a lot. That's going to have a lot of linolenic acid. So that's pretty much the story on triacylglycerols. So this went fairly quickly. We're going to continue in a moment here on with section 15.4. And here we are at section 15.4, which is, again, going to be chemical properties of triacylglycerols. We've said about all we're going to say about waxes, and we need a little bit more to say. We need to say a little bit more about the chemical properties of triacylglycerols. And this is largely the the non-biological chemical properties, but they are important industrially to a large extent. You've heard of margarine. You've heard of solid shortening. Partial hydrogenation of vegetable oils is what they are. You take vegetable oils, you add hydrogen to the double bonds, you now have saturated fatty acids, so they're going to be solids. Pretty as simple as that. And they want you to learn to do the structural formulas of the products of the triacylglycerols after undergoing hydrogenation, and also hydrolysis or saponification, which is a form of hydrolysis. And we'll see what they are shortly. Hydrogenation is the, I guess maybe the simpler of the two. You have a double bond and you have hydrogen, and they have nickel here. There's a number of catalysts. You can do this with nickel's a common one. You have the fatty acid in a container, and it's in contact with this nickel catalyst, and you have hydrogenation. You have hydrogen being pumped in there, maybe bubbled through the solution or just under pressure. But what's going to happen is these double bonds are going to absorb the hydrogen. They're going to react with the hydrogen to form, one double bond is going to react with one molecule of hydrogen to give you two carbon-hydrogen single bonds. So you now have where you have unsaturation to start in the starting material, you now have saturated material in the product. And you see there's glycerol trioleate or triolean. I forgot to mention when this in naming these, there's glyceryl trioleate. That's one way of naming it, but then there's another system of naming it where you take the tri and then the fatty acid, you remove the oic acid and add EN or something like that. Okay, so triolean, trioleate, glyceryl trioleate, triolean are going to be the same thing. When you hydrogenate this, you end up with glyceryl tristearate or tristearin, which now is fully saturated. And of course, triolean, glyceryl trioleate, is going to be a liquid at room temperature, and tristearin is going to be a solid. We know that. That same reasoning, again, the same reasoning with the fatty acid melting points holds for the triglyceride, the triacylglycerol melting points. And one of the points that is probably good to take away from this course is that you're learning a lot of correlations between properties, structure, and properties. And these are, when you do chemistry, that's what chemistry is all about, really. How does the chemical structure affect the properties? And a lot of times the same reasoning is going to cross over to a number of different sectors, a number of different types of compounds, a number of different things. You're going to see that time and again, even the rest of this course. So hydrogenation reactions commercially, they're not gone all to completion, because if you had just everything, if everything's saturated, you're going to have this chunky stuff that isn't really going to be good for much. You need to have some, like margarine. You want this, buttery kind of feel to it. You don't want these clumps are almost powders of, being their, well, it just wouldn't be very useful for the application. And here's a little something from personal experience, actually. That was at a little coffee hour at one time, and it was people bake things, baked pastries and brownies and donuts and biscuits and various things. Well, somebody actually took almond butter and used it to I think it was almond butter, but used it to replace a different kind of vegetable butter, which was called for in the recipe. Well, it didn't really turn out very well. And the point I'm making here is these things are not all the same. We have the triolein going to tristearate. Okay, that's going to be tristearate. But then you take various vegetable oils. You take corn oil, you take soybean oil, you take almond oil, you take any of these oils, and you hydrogenate them partially. You get these semi-solid masses, but they all have different distributions of fatty acids, which means their properties in use in foods is going to vary quite a lot. And sometimes they'll work out, and sometimes they won't. You really don't want to substitute these things unless you've actually tried it first. So that's just something to keep in mind when we say butter. We don't really, there's different kinds of butter depending on how they're made, and margarine, what it's made from. And well, you probably understand cheese. There's a lot of protein in cheese, but there's also a lot of fatty acid, a lot of triacylglycerols. And I think having tasted a number of different cheeses, you realize that the composition, whatever milk is being used for these things, is going to have a large effect on what comes out. Of course, naturally, how these things are fermented and all. All right. What are the products of complete hydrogenation of triglycerol-oleate? You can think about this. Now, I'm just going to go ahead and explain this because I can't ask you. I don't have a class out in front of me. But you can stop. You can stop the recording. You can stop the tape. You can stop the video and think about it. What products are obtained from complete hydrogenation of glycerol trioleate? Well, you have a choice. Glycerol and 3 oleic acids, complete hydrogenation now, okay? Triglycerol stearate, glycerol and 3 stearic acids. Now you see what this question could throw a few people, okay? Glycerol and 3 oleic acids. Well, you know that hydrogenation reacts with the double bonds in an unsaturated fatty acid to give you, 2 more carbon-hydrogen single bonds. You're not going to have a double bond anymore. It's not going to be unsaturated anymore. So A is out. A is completely out. On top of which, this isn't a hydrolysis. They don't say anything about acid or base. And then C, as I just said, you're not breaking the triglyceride apart. You're just hydrogenating the double bonds. So it has to be glycerol tristearate, and you know that glycerol trioleate with oleic acid residues on it, C18. Once those are saturated, they're going to be C18 saturated, and that's stearic acid, so it's got to be B. That might be the kind of reasoning you'd use, and of course it is B. Another issue, moving along, unsaturated fatty acids naturally occurring are usually cis. Remember we talked about the kink in the molecule that makes it makes the molecule unable to fit into a solid. You don't get the dispersion forces. You don't have the these long chains lining up and getting what they might call hydrophobic interaction as well. That doesn't fit. It just doesn't fit into a solid real well. It doesn't hold together real well. The cis double bond. Well, trans double bonds are a little different. You don't really have that kink in the chain, and so there's another issue that trans double bonds, trans fatty acids, are bad. I mean, there's health issues associated with them that you'll see on food labels. They might give you some comment about whether or not there's trans fatty acids in this stuff and how much. And well, remember we said that you don't hydrogenate oils completely to get like a margarine, something like that. But what can happen is this hydrogenation reaction. When you have that catalyst in there, the nickel, and there's other catalysts as well, the reaction can reverse. So you're going to have hydrogen adding to double bonds, and you're going to have a little bit of hydrogen being removed to form double bonds. And when that happens, you're going to be seeing trans fatty acids for the most part. So you have some, and actually you can have an intermediate in a step in a hydrogenation reaction that doesn't go all the way, and it kind of reverses itself, and what you end up with is you kind of break the double bond a little bit, and then the chain rotates, and then it reforms the double bond in a trans configuration, and you've got a trans fatty acid. You see the estimates here. They behave like saturated fatty acids because I just mentioned they're more linear. They don't have the kink in them. The double bond doesn't really affect the shape of the molecule compared with the saturated fatty acid. Doesn't do it all that much. And it raises the LDL cholesterol and lowers the HDL cholesterol, which isn't a good thing. And there's probably a few other things that they do that aren't particularly too good. So here's basically the reaction, hydrogenation of trans fatty acids. You see you have a cis fatty acid, and if this thing goes to completion, you have a saturated product, but if it reverses, you can isomerize this, and you have it where you started with a cis fatty acid, you now have a trans fatty acid. And it could be either a reversal of the process or just what happens is the hydrogen is adsorbed on the surface of the catalyst, and it's more reactive in that form, and the double bond gets in, and it reacts partially. Okay, so you have a single bond in there, and the second hydrogen really doesn't get a chance to get on when the configuration changes, and then it comes back off as a double bond. So, but you're going to get this anytime you have hydrogenation. Trans fatty acids. Well, here's how you get the stuff. Food, some occurs naturally, milk, eggs, beef, and you get foods from the hydrogenation process, and then you have anywhere you bake or fry these things, or they stick in soft margarines, and then they mentioned vegetable shortening. These are all margarines are hydrogenation products, and so is shortening. So anytime you have that process, you're going to get some trans fatty acids. And then these deep fried goods and baked goods, heating a fatty acid to a high enough temperature is going to allow you to do some some rearrangement, some isomerization there. So it can happen that way as well. So there's heating it and hydrogenating it. Partial hydrogenation is going to give you trans fatty acids. All right, let's do a learning check here. Which of the following statements are true and which are false? There are more unsaturated fats in vegetable oils. Is that true? Vegetable oils have higher melting points than fats. Is that true? Hydrogenation of oils converts some cis double bonds to trans double bonds. Is that true or is it false? Animal fats have more saturated fats. Well, going down one by one, vegetable oils are characterized for the most part by unsaturation. Unsaturated fatty acids. The names of all these oils, all right, corn oil, safflower oil, linseed oil, soybean oil, and so forth, they're unsaturated. They're oils. They have largely unsaturated fats. There are a couple of oddballs, but that's usually true. Okay. Vegetable oils have higher melting points than fats. Well, we just said that vegetable oils have more unsaturated fatty acids. We know that unsaturated fatty acids have lower melting points, so B has got to be false. We have hydrogenation of oils converts some cis double bonds to trans double bonds. We just talked about that. That was the last thing we talked about, so we know that's true. Animal fats have more saturated fats. Well, that is true as well. So we have, let's see what I work out here. Unsaturated fats, more unsaturated fats, true. Higher melting point, true. Or wait a minute, more unsaturated fats in vegetable oils, true. Higher melting points in fats, no, that's false. That's false. Okay. Okay, so we got true, false. Convert some cis double bonds to trans. That's true, true, false, true. Animals, that should be 3 trues there, it looks like. So we got that one right. And, well, there's a third learning check here. So let's take a look at that. Draw the condensed structural formula for the product of glycerol tripalmitoleic that undergoes hydrogenation. And I put a couple of videos on the drawing program, and they deal with something like this. And I don't remember, I think it's a hydrolysis reaction, but all the same, you have to they have you draw all the structures. When they tell you to give you all the products, all the reactants, whichever it is, you want to make sure you have all of them in there. Anyway, what's the product of the glycerol tripalmitoleic that undergoes hydrogenation? Okay, we just talked about hydrogenation. You know what that is, right? You're adding hydrogen to double bonds. You're going from an unsaturated to a saturated molecule. So whatever's coming out of this is going to be all saturated. And it's tripalmitoleic, so it's going to be tripalmitin. Yeah, palmitic acid, yeah. So, or glycerol tripalmitate. Okay. So all you really need to do is draw this thing with, well, you really aren't going to have any, you're only going to have one product. You're just going to have the triglyceride. So you have the three, you're going to have the one molecule of glycerol tripalmitoleic, and for each double bond that's hydrogenated, you're going to need one molecule of hydrogen. So you've got 3 double bonds, you're going to need 3 molecules of hydrogen. So you draw those. So you've got that. And you see you've just saturated the double bonds. So now you have all these residues are palmitic acid residues. So glycerol tripalmitate is what that's going to be. But that's going to be the reaction. It's complicated drawing it out, but the only thing that's happening is the double bonds are going, you're adding hydrogen to the double bonds, so the hydrogen's going away, the double bonds are going away, and you have the saturated fatty acids here. So hydrogenation, that's one of the reactions. There's also hydrolysis. You should probably remember this from when you were talking about esters. We saw some things about esters. You have strong acid and water, and you cook the triglyceride with this, and you're going to hydrolyze it to glycerol and the fatty acids. Okay, so, and you saw this in the hydrogenation problem just a couple slides ago, where you have one molecule of hydrogen is needed for each double bond, and the tripalmitoleate, the glycerol tripalmitoleate had 3 palmitoleic acid residues, which means it had 3 double bonds. So one molecule of the triglyceride required 3 molecules of hydrogen to fully react. The same thing is true here. You have 3 ester groups. And so you're going to need 3 water molecules. And you see they set this up so that you can see where these things are coming, how the hydrolysis is taking place. Okay, so you've got an ester, you've got esters here, and then you're going to react. You're going to have a part of the water molecule is going to go with the palmitic acid as the OH, and then the hydrogen from the water molecule is going to go with the alcohol, which is the glycerol. And it's going to happen 3 times, so you can get the whole thing hydrolyzed. This is reversible, by the way. In fact, you can make esters this way by setting up the reaction in such a way as to remove the water from the reaction mixture, so it can't reverse because there's no more water around. Saponification comes from a word having to do with soap, and in fact, there's traditional ways of making soap are like reacting fat with wood ashes, which are very basic, and they do this reaction. Well, this is a reaction with a strong base. So we come back here. You notice you're getting an acid out here. You're getting 3 molecules of carboxylic acid, palmitic acid in this case. And you're an acid, so very strong acid. So this, and you know that carboxylic acids are very weak acids. So in water, this does not dissociate very much. In a strong acid, it's going to dissociate even a lot less. So you're getting palmitic acid out. If you do it in strong base, you get glycerol and you get the sodium salts of the fatty acid. Well, if you're using sodium hydroxide, you get the sodium salts of the fatty acid. You could use potassium hydroxide, in which case you're going to get the potassium salts or calcium hydroxide, probably a few others. And you form soaps, which are salts of fatty acids. And pretty simple process. You got sodium hydroxide or potassium hydroxide. And, well, sodium hydroxide is going to give you solid soaps. They can be molded. They can be put into different shapes. Potassium hydroxide, you get liquid soaps. It's just a simple difference. So the bar soap is going to be mostly the sodium salts of these things. And, soft soaps are going to be more liquid. And also just a couple of things. There's a lot of cleaning solutions. Cleaning materials are not soaps at all. In fact, you have detergents, which are something different. They all behave similarly, but there's these liquid soaps. I just took a look at a couple of these. that we have at home, and they didn't mention anything about any sodium or potassium salts. And I found an Irish Spring is mentioned. It was nothing but there were several sodium salts, and there was a shaving soap that had kind of a mixture of the two. So you can take a look at some of the labels on soaps that you might have. You'll probably, if they're solids, you're going to see some potassium salts, or if they're liquids, you can use other things besides soaps for cleaning in those cases. But soft soaps are going to tend to be potassium or liquid. Reaction looks like this. It's similar. You have a strong fat or oil, strong base, and you have glycerol, salts and fatty acids. This actually, you've heard of biodiesel. This is sort of how it works, except that instead of this sodium hydroxide, I'll show you this. I'll have to insert something here. What happens here is where you don't have sodium hydroxide. What you do is what you're really going to have is going to be this. I'll try to insert something here. You'll have, try to open this up here. That's not working. I want to get a text box in here. No, wait, I see. There we go. Nope, that's not working. Try it again. Here we go. You're going to have, rather than sodium hydroxide, you're going to take methanol, and we take methanol and sodium hydroxide. There's a little bit of or you could actually get a hold of sodium methoxide by itself. It looks like this. OCH, and that looks like it comes from methanol. Okay, methanol, alcohols can act as, like water, that dissociate, and you have strong base in there. You get this methoxide, and what you're going to end up with is, rather than this mixture of the sodium palmitate and glycerol, if you're using sodium methoxide, what's going to happen is you're going to have the glycerol, but you're going to have the methyl ester of palmitic acid. So that's really what's going on with biodiesel. That's the way the reaction works. So I thought I'd throw that in. Okay, so the summary of these are the reactions we've talked about. You know about esterification. We've talked about esterification previously, and you take a carboxylic acid and water, an acid and heat, you get an ester, or carboxylic acid and an alcohol. You react with acid and you heat it, you're going to get an ester and water, and that's going to be in equilibrium. It's going to go both directions. There's Le Chatelier's principle, where if you stress a reaction, it's going to act as to reduce the stress. So if you're making a fairly high boiling ester, you can heat the thing up, and you can find a way of there's ways of removing water. Okay, you remove the water, and it's going to drive it towards the ester. Otherwise, it's going to be in equilibrium. When you esterify, you're going to take 3 fatty acids plus glycerol, and then you're going to get 1 fatty acid molecule, which is going to be a triacylglycerol, and 3 water molecules. In hydrogenation, we saw that you're adding hydrogen to a double bond. You're getting an unsaturated fat from that plus hydrogen. And of course, we talked about partial hydrogenation, where you're going to get the trans isomerization of fatty acids, which is undesirable. But it's going to happen. Hydrolysis, we saw hydrolysis as ester and water, which is just the reverse of the carboxylic acid reaction, of the esterification reaction. So you're going to get you're going to take like triacylglycerol, and that's hydrolysis, and then you're going to get 3 water molecules plus 3 water molecules, and then you're going to get 3 fatty acid molecules and glycerol. So you're going to start with, well, 4. Well, you end up with 4 molecules to start and 4 to finish, but you've broken down your triacylglycerol completely here. And saponification, you're doing essentially the same thing with a base. This one's not reversible. Once this goes, you've got a salt of a fatty acid, and that's a soap. A sodium salt of a fatty acid or a potassium salt is a soap. So keep those in mind. So what are our learning checks? Okay, write the equation for the reaction catalyzed by the enzyme lipase that hydrolyzes glycerol trilaurate, which is trilaurin. You should be able to write that if asked. Of course, they have it right in front of you. During the digestion process. So this is going to be an enzyme reaction. There's not going to be any, well, if this is whether it's acid or basic, it doesn't matter. It's the lipase is going to break this thing down. So this is kind of neutral, under neutral conditions. And you're adding water, and you know what a hydrolysis reaction is. So you're taking the glyceryl trilaurate. You see there's the 3 ester bonds. They're going to be hydrolyzed. This is going to pair up with a hydrogen to give you, of a water molecule, to give you an alcohol group, hydroxyl group. This is going to pair up with the OH from water to give you an acid. And you're going to see the 1 glycerol molecule and 3 fatty acid molecules. Keep those in mind. Okay, that's going to be all for this particular session. I'm going to do another one and complete. I don't know if I'm going to do the rest of the chapter in 1 or 2 videos, but I'm done with this one. I'll put this thing up and it'll be available to you.